you probably only have to work with graphs for a very short time before you immediately start thinking about algorithms on graphs. And there's a couple reasons for this. One is that many of the basic facts that you're going to prove in graph theory are proven by actual constructions. And those constructions are algorithms, and then you prove the correctness of the algorithm to prove the correctness or the truth of a theorem. And so algorithms come up all the time. But the other way they come up is that, well, there are many concepts in computer science that are naturally modeled by graphs, and you immediately end up with graph algorithms when you try to solve problems related to whatever those concepts might be. So there are a lot of algorithmic problems, and if you want to get at least started actually writing code to solve some of these problems, the first thing you're going to need is a data structure. So let me walk through. I'm going to do kind of a live coding. It's somewhat prepared, but it'll somewhat off the top of my head here, just kind of how you might go about constructing a data structure for a graph that's pretty efficient for representing the main ideas we've seen so far in graph theory. And this is also going to give us a good way to solidify our main definitions. So you really know you understand the definitions if you can implement them in some programming language. And we're going to use Python here. So let me pull up a code window. All right. So this is Python. So I'm going to make a class for our graph. So if I'm going to make a data structure, generally I want it as a class. And I need to initialize it. And well, the definition of a graph is just what? A set of vertices and a set of pairs of vertices. So it's a set of vertices and edges. So let's just pass vertices and edges to my graph. And before I actually even write out what I will do inside it, let's get an idea of what we're actually going to do with it when we have it, right? So if you write code to use the code before you actually write the code that you want to use, this is a great way to get an idea of what code you actually need to write. So I'm just putting this little standard Python idiom, if name equals main, this way. If we like this library and we want to import it later, this code will not get run. It will only get run when I run it here. So what I'd like to do is I'd like to be able to create a graph just like this and pass it some vertices, like 1, 2, 3, and some edges. And I guess the edges will be like tuples is the easiest way to express some pairs. So 1, 2, and 2, 3. So this is a graph with 3 vertices and 2 edges. It's actually just a path of length 2. Okay, and I can run this, and it ran, which is maybe not surprising, but it's also not so interesting. Let me see if I can get the bottom here to show. Can you see that? There we go. So you can see the bottom there. It says it finished in 0.05 seconds. So great. It ran this code, but doesn't really do anything interesting yet. All right, so I want to store the vertices and edges. So the simplest thing I could do is something like this. This is not so good. Let me give you a couple reasons. One is that, well, the vertex set might not actually be a set. Someone could have given me a list here. In fact, I should be okay with that. Like if it gives me a list, I should be okay with this too. But I kind of want the internal representation to be a set, because if I want to add a vertex or remove a vertex, I just want to, or even just tell if a vertex is in the graph, I want to be able to do that quickly, and so having it in a set makes the most sense. So the only assumption I'm going to make is that it gave me some iterable collection, right? Something I could loop over, and so that I can turn that into a set this way. And you might think I'd want to do the same thing for E, but there's a bigger problem with the edge set, because the edges are actually supposed to be unordered pairs, and what I gave it was ordered pairs. Now, you might think, oh, we'll just replace those tuples, those parentheses, with curly braces and make them sets. If you think that's a good idea, I can do it here, but many of you know that I'm going to get a little bit of I'm going to run into some trouble here, because when I run that, it gives me a syntax error. Oh no, syntax error, that's not the one I expected. I expected a whole different error. Here we go, unhashable type set, right? You can't have a set of sets. So let's back that up. Let's go back here to this set of tuples, but we're going to have to kind of turn those ordered pairs into unordered pairs, but we still want them in a set. So there is a way to do this. You just make a frozen set, which is a Python data structure that that stores a set, but since the set can't be changed, it's immutable, it can also be hashable, and so you can put frozen sets inside a set. Okay, so this will not work yet, actually. I think if I run it, I'll get an error because it says I passed too many arguments, right? Because this has to be some kind of iterable collection itself. And I run it. Okay, there we go. So what I've done here is that I gave it some vertices, some edges, and it just took the vertices and edges and sort of repackaged them up internally, which is a good thing to do generally. So if I have a graph, like the easiest, kind of simplest questions you might ask to be able to, like the information you'd like to be able to get out of the graph might be something like maybe the degree of a vertex. Let's try this. So let's implement degree. So I want to know the degree of a vertex V. And right now, I think what I'd have to do is something weird, right? Like I have to iterate over all the edges and add up the ones that contain V, right? And if I want to, so I can like add one for, I guess for edges in self.e if V is in that edge. This is like, is that too fancy? That might be too fancy. I feel okay writing this kind of weird, fast one-liners that are a little bit cryptic because we're going to throw that away because it's actually not such a good way to implement this. But let's do it as a first cut. Let's at least make sure, see if it works. What do we expect to see? If I get the degree of vertex 2, I think I expect it to print a 2 here. Let's see. It does. Good. All right. So what about degree of 1? Yep. Prints that. And degree of 3. This should also be 1. And there you go. All right. So it seems like it works. But like I said, it's not so nice. It's not just not nice because I've written a somewhat cryptic one-liner here. It's also not nice because in order to get the degree, I actually had to loop over every edge in the entire graph, which is obviously a bad thing. So if I wanted to do this quickly, I probably want to represent things a little differently internally. And, many of the things we do with graphs, because the graph is representing local connections, we often just want to make local jumps. Like we'd like to take a vertex and ask what other vertices are adjacent to that vertex. That is, we want to know the neighbors of a vertex. And if we could just get the neighbors, then maybe we could easily get the degree, right? We could just count them. And this turns out to be a really nice way to represent a graph. So let me just add this in. So even though I initialized the graph with just a vertex set and an edge set, internally, I'm going to store all these adjacencies. And the way I'll do it is I'll make a little dictionary. And the dictionary is going to map vertices to sets. And every vertex will be mapped to its neighbors set. So a set of neighbors. So that's just a dictionary like this. And so for each one of the vertices, and I guess, well, really what I want is that for each one of the vertices, I'm going to initialize this. Neighbors V is just going to be initialized to be an empty set. And then for every one of the edges, I'm going to have to add 2 entries into this dictionary, right? So, where I'm going to add for each end of the edge, I'm going to add the other one into its neighbor set. So it looks something like this, right? So for UV in the edges, we're going to have self.neighbors of U add V and self.neighbors of V add U, right? So the neighbors of U is a set, and I've added V to it. And the neighbors of V is a set, and I added U to it. So I have here then my new representation here. And now I think I can simplify this to be something more like, let's just return the length of that set. So If I run it, okay, I got 1. That's what I expected. In fact, if these are expectations, let me just write them as assertions. So I'm going to assert that the degree of 1 should be equal to 1. Assert degree of 2 should be 2. And this one, assert that the degree of 3 should also be back to 1. And I like to do the following thing. If I put a bunch of assertions in here, really I should wrap them up into some tests or something, but I like to print something so I know that they actually got through all the assertions and it actually ran. And so everything seems to work now. Okay, so this is actually a very basic and functional, completely functional implementation of a graph. And you can get pretty far with this, actually. Although, in terms of using it from the outside, that is, like if I create an instance of a graph and I want to then run other algorithms on it, it would be pretty handy to have access to the neighbors. Right now, I put the little underscore there because that data structure now is kind of internal to the class. It's private as far as things can be private in Python. But I want to give access to that without actually giving access to the data structure. So what I'll do is I'll just actually add a method here. So and I'll call it neighbors. And so if I want the neighbors of a vertex, it can return, I could just return the set of neighbors. This makes me a little uncomfortable. I kind of am a very private person when it comes to my data structures, and I kind of prefer that if a user of the data structure shouldn't be able to mess around with the internals. So I might actually, instead of giving them the set, I might just give them an iterator over the set, so they can't actually change anything. It's sometimes for their own protection, okay? And now I'm going to also, I want to clean this up a little because we have some operations that we would want to do on a graph, like building it one step at a time, like adding one vertex at a time or adding one edge at a time. And it's pretty clear to me, at least, that as soon as I have this method, even before I've written any other code, I have a use for it. So if I want to add a vertex VA to a graph, then I know that I'm just going to have to add it into this vertex set. So it'd be like self.v.add v, big V to little v is being added to the big V. And then I need to create some neighbors for it, right? So this is what we did here. And I could do the following now, is that instead of doing this, for every vertex that got passed in, I could just add the vertex. Okay. All right, so this almost works, but there's something a little scary about it as well, because, you know, someone might add the same vertex twice. And if they later add a vertex again, I kind of don't want it to destroy, like eliminate all the neighbors that were already stored in this dictionary. So I kind of want to make sure I don't overwrite things. Maybe we'll get to that. But there's something else awkward about this. So I have a set with all the vertices in it, but I also have a dictionary whose keys are all the vertices. So this is really redundant. I actually don't need both. If I want the vertices, I would just look at the keys in this neighbor dictionary. So I can get rid of this, which seems a little nuts because, man, if I'm going to store the vertices, you would think that in this data structure I'd have the vertices. But instead, I have them just as the keys in a dictionary, which map to the neighbors. And so this kind of idea of storing just the adjacency is called the adjacency, sometimes called the adjacency set. It's a variation of the adjacency list. There's also adjacency mapping. But there's many of these kind of data structures where you just store the adjacencies, usually in some kind of dictionary-like object. I'm not going to fix this problem with adding vertices more than once. You'll notice that adding edges more than once is really okay. Because it's a set, the edges are a set, and the frozen sets, you know, if I add the edge more than once to the same set, I still only have one copy of it because there are no duplicates in a set. And the neighbors are stored as sets too. So if it gets added more than once as a neighbor, it still only appears one time because, again, sets don't have duplicates. So we can get pretty far not thinking too much about those corner cases here. But really, this kind of stuff should be also packaged up, I think, in a separate method, which we'll call add edge UV. Okay, and let's do that. So add edge UV. Oops, we need to include self, right? So we pass the graph object itself, and the two vertices that we're going to connect, U and V. And that's it, right? So we add them in here. Now, one weird thing about this is technically I can call this add edge method even if I haven't added the vertices. I could check to make sure that the vertices are there, because if I try to add an edge and the two end points of the edge are not already vertices in here, I'm going to get a key error because it's going to look up for the neighbors to try to add a new neighbor, and it will get a key error. It won't find that vertex. So I could do something like this. Like if it's not in there, then I can add it. And I think this is kind of the right behavior. I think if you try to add an edge and you haven't already added the vertex, you might as well go ahead and add the vertices, because it's much more likely that that's the desired behavior here. And I could do this again for V, but it's maybe let's just go ahead and re-add the vertices, and let's figure out what to really do about this case of adding in a new vertex if it's not already been added. And I think the easiest thing to do, oh, and I can get rid of this line too, right? This line is done because we don't even have self.v. So I'll just make sure if I haven't already added it, I'll add it. And if it's already been added, I can just skip it, right? So if it's in there, it'll be in the dictionary already. So actually, if it's not in there, then I'll create it. Otherwise, I'll just move on. Piece of cake. There's a built-in Python method on the dictionary to do this kind of default setting. It does essentially the same thing, but that's all. So I think this will do. Let's just make sure that at least the little bit of code I have here at the bottom actually runs. It doesn't. It says it's looking for V. I must have left in one of my, yes, right here. This should just iterate over the input. Let's try that. Boom, okay. Good to go. All right, so what can we do with this? We have a graph now. It stores the vertices and the edges. I can get access to the degrees, and I should, in theory, be able to get access to the neighbors of any vertex. Let's make sure I can actually do that. So let's just see, what do I get if I print g.neighbors of 2. It gives me a set iterator object. Oh, that's right, because I only gave you an iterator over it. So let's just put it in a list and print it out. Boom. Okay, 1 and 3. So if the neighbors of 2 are 1 and 3, the neighbors of 1 should just be 2. The neighbors of 3 should just be 2 also. Good. So there we go. That is most of the public interface for a graph that we might want to use. I'll just put this one in here. In fact, let me put it as a set. That way I can check equality and I don't have to worry about the orders. And of course, those are not the right neighbors. It should be 1 and 3. All right. So, so there we go. Maybe this is good enough for now. I can create a graph. I can add a vertex. I can add an edge. I can get the degrees. Any other good stuff we would like to do? I guess I would like to be able to know how many vertices and edges I have. For a lot of times, you may see cases where this this edge set is not explicitly stored. Like I can actually get away with not storing this self.e, so the graph doesn't have a special lit set of edges somewhere. But I kept it around actually for exactly this one reason, which is that I would like to be able to get the number of edges, and the edges are almost always called m, and so I can return the length of self.e, right? So this data structure right here tells me how many edges. If I didn't have that and I had to figure out how many edges there were just from the neighbor dictionary, I think I would have to iterate over all the vertices, add up all the degrees, and then divide by 2. And that takes way too long to just give me the number of edges. So here I have this. And actually, if I'm going to use it, I'm going to make this a property so that I don't have to put parentheses every time I ask for it. Right? G.m is going to be the number of edges. And similarly, I'm just going to do the same for vertices, which is should just be called n, because n is always going to be used to be the number of vertices in the graph. And let's try that. This should be what? Length of this neighbor dictionary, right? Because the number of keys in the dictionary, there's one key for every vertex, so that should do it. Let's check. I believe what should be true here, we should have g.n equals 3, and g.m is equal to 2. So, okay. All right. So I can get number of vertices, number of edges. I can add edges. I can add vertices. I can also remove stuff. Let's do that as well. If I want to remove a vertex or an edge, which one is easier? I think removing an edge is way easier. And the reason is that when you remove a vertex, it also has to remove some edges, so it'll be much cleaner for us to be able to already remove edges before we get to vertices. So if I want to remove an edge, okay, what do? I guess I want to take the edge set and remove, well, I got to package it back up into UV. And I guess I need this as well. Okay. Now, that's not enough because in U, I've got the neighbors of U contains V and the neighbors of V contain U. So I have to remove both of those as well. Okay, so I would go into the neighbors of U and I'm going to remove V, and I go into the neighbors of V and I'm going to remove U. Okay. This is okay. We could test it at least, see if it makes sense. For instance, right here, I could do g.remove edge 1, 2. And it runs without error. I think what I expect to see here now is that the number of vertices should still be 3, but the number of edges should be 1. Okay, and that's true. The thing I don't know right now is what if I remove an edge that's not actually there? I think this should fail, right? Because I get a key error. It looked for the edge in the set when it was trying to remove it, but didn't find it. So we might as well check it first. And I think maybe we could just do this in 2 steps here. Let's package up this edge. There it is, the frozen set. Let's call it E. If E is an edge, then I could just check it this way. And I'll only do the other stuff if it actually was an edge. If it wasn't already an edge, then I got nothing to do. I can just return. And so there you go. Now I can remove an edge, and if I want to remove a vertex as well, now what I'll do is I'm going to just iterate over all its neighbors, which I can do because I can actually use the public interface here. I can just iterate over the neighbors. And for each one, I'm going to remove that edge. And then finally, I'm going to remove the vertex. So this should be straightforward. So for every vertex in self dot, let's do it like this: neighbors of u. I could also use the private dictionary here and write this as neighbors of u. But I think it's a good practice whenever possible to try to use the public interface. So let's do that. So neighbors of u. Because the public interface tends to be more stable, so if things change, you're much more likely to have fewer changes to make. All right, so for every vertex that's a neighbor, I can just remove that edge. Let's do that. Remove edge u to v. There we go. So this should take a vertex and just remove all the edges coming out of it. And now it'll be an isolated vertex. And now we're just going to have to pop that out of the dictionary. And to remove something from a dictionary, I think you have to do this. So let's do self dot neighbors u. Now, you might think, why not just do this one here, right? Because if it removes that, it removes everything, all its neighbors. We would still have to go back and remove the edges coming in, right? So from all the neighbors v of u, we'd have to still remove u from their neighbor list. So this is kind of just a clean way to do it. It's not the most efficient because it's sort of removing one by one all the neighbors of u and then just deleting the whole set. But in terms of being readable and hopefully idiomatic and clear, I think this is pretty straightforward. All right. So okay. So I didn't actually call this function yet. So let's do it. Let's do. Let's actually. So first of all, let's check. Removing edge 1,3 actually is still okay. I don't know if you caught that, but it runs now because it didn't actually do anything. It still has this one edge and 3 vertices. In fact, let's put the edge back in, the one we took out, 1, 2, and then right. So we put it back in, and we should check. It should have 2 edges again. No, it doesn't. Interesting. It doesn't have 2 edges. Why not? What are the edges? It only has the edge 2, 3. So add edge is not doing what it's supposed to. Why not? Yeah, add edge should probably add it to this set E here. So let's do that. Let's make edge UV and add it in there. Okay, and again, we don't have to think too hard about this right now. If it was already in there, we could just skip it. And if we add it again, it's a set. It won't cost us anything. All right, so now it runs. It has the right number of edges here. And so I'm back to a path. It should go 1 to 2, 2 to 3. And I think if I did g.remove vertex, I want to remove a vertex with more than one edge coming out. So let's do that. And I think what I should have now, if I remove that vertex 2, I should have 2 vertices, 1 and 3, and no edges at all. So g.end should be 2, and m should be 0. And oh, it's no good. Oh no, I've done something terrible. I actually manipulated a set while I was iterating over it. So you see this runtime error, set change size during iteration. Yeah, can't do that. So where did I go wrong? I think it's right here. You see, this remove edge function actually changes self.neighbors, and neighbors is iterating over it. So we have to be a little bit more careful here. Let's, I could just pull them out like this. So I can make just a list of vertices to remove, that is of neighbors. And then I can iterate over that instead. All right, so that way I did one iteration to get all the neighbors. I've got them, and now I'm hopefully this will work now. Okay, so you do have to be careful about when you're editing sets that you're not also iterating over that set at the same time. All right, this is pretty good. All right, let's just recap it. So we can build a graph from vertices and edges. We can add an edge. We can add a vertex. We can remove a vertex, remove an edge. We can get the number of vertices, number of edges. There's n and m. And we can get the degree of a vertex. And we can also get the number an iterator over the neighbors of any one vertex. It turns out that this gets you most of the way to being able to implement most of the kind of standard data structures you'd like to be able to implement. And in another video, I'll actually show you how to implement some basic ones and some fun ones. So we'll get to that pretty soon.